team from here we want to discuss with you the smart cop problem because we found some solutions to it and we'd like to know if there are any other solutions. First, the huge question of the problem is the human ear can determine the speed of a moving object, for example a car, just hearing the sound that it produces. This is the scheme for the presentation. Well, so this is the situation. We have a cop somewhere near to the road, and he wants to determine the velocity or the speed of the car. And we have to think about two things. The first one, the cop shouldn't be on the road because he wants us to get rolled out. And the second one is that the cars used to get sort of constant speed, high velocities. That's what the cops want to know. This is a cop, right? So this data from this reference and several other references shows this. There are other things that we have to think about, and there are many sources of sound that can be taken into account for a moving car. There is the sound of the engine, there is the sound of the tires with the road, there is the sound of the wind crashing with the car, and sometimes it's some other kind of noise sources, as some other parts of the car, like the landscape, etc. First, we have to think about how the human ear processes the sounds. First of all, our ear have to filter the sound with a special shape. This is how the human ear appreciates the sound. Well, we can see that all the frequencies does not have the same perception for the ear. So if you want to know what actually the human ear hears, we need to filter it or use the GBA or some awakening process in order to do this. Another important stuff to take into account is that the sounds of the human roughly differences 3.8 Hertz for low frequencies and from above 500 Hertz, and from above 0.7% from the emitted frequency. Another stuff to take into account is the binaural hearing. The human ear, of course, can detect, can localize sounds just by hearing. You can just close your eyes and try to figure out where I am. Well, actually, with these walls, probably you would not do that, but in a novel field, you probably should do that. And we have two principal parts of this, and there are the interannual intense difference and the interannual time difference. Here we can see that the sounds that arrive to this here will be different to the time that arrives this year because the difference of length between the two beams of sound, if you think of that way. And also the intensity difference will come because here the head somehow absorbs some part of the intensity, so there will be intensity difference. Another thing interesting found in references is the time. The time is very important to this. The more the time, so more accurate will be our ear to localize the sound, and this will become by the just notable difference of the sound that will be here. So changing the angles, our ear will detect this intensity difference and time differences. We can see from different frequencies this will change drastically, and we also can see that from 0 and 180 degrees, the ear is not so good at differentiating sounds. This is come from 0, and this is one, if my head is looking that way, 108 degrees. So we propose 3 models to do this. The first one is, well, as physicists, the first thing we thought about this was the Doppler effect. And using Doppler effect outside the axis of movement, we found this expression can be found. We found that expression, and with these angles. And for binaural hearing, just doing simple math, we can found this. This is for constant velocity, constant speed, which is state that the cars used to do that. So our experimental setup is just simple. We have a straight road with the car, and we have 4 chronometers that will be synchronized with the computer chronometer with open the microphone, the omnidirectional microphone cardiac, and we just hear the car passing by. And with knowing the distance from these chronometers, we can know on the record which time is for each lap. Also, for binaural perception, here are like 7 meters. We moved bass amplifier through this straight line, and we put some subjects of the test in persons to determine with a draw protractor the angles that they thought the object was. Of course, they didn't see where it was. So, for the first model, we found this graph where the purple line is due to the noise of the signal for the place that we were, and the other 3 for 3 different distances. We tried to analyze it, but we didn't find actually conclusive result to watch the Doppler effect in any of these spikes. This is the Fourier transform for a time interval, a linear time interval. Although we found an interesting phenomenon in such different cars. We tried 5 cars in almost all of them. We found this sort of a peak around. Sorry, the numbers can be seen, but this like 15,000 hertz, and we didn't know what it was, but it was in every measure. We didn't know if it was noise, because it can be noise, but we actually would like to know if you found that maybe it's a common sound from the other cars, like the tires with the road, that is really similar, because all the other cars has almost the same tires. So that was an interesting phenomenon that we found. So from binaural hearing, using the velocity expression, we found this data. We approximate it to we fitted it with a straight line, which have a good correlation. Besides, our protector has 5 degrees of measuring. Yeah, so it was not so good. But besides that, taking into account that the data was so good, I mean, all the subjects tend to know where the car was, and from velocity we can see that data starts to spread. But we also have to take into account that we have to make more measurement, because we need more data to conclude that. The percent of average error is like 23%, and the best subject has 2% of error. The third model that we didn't test was about intensity. We found actually a mathematical expression that relates the sound, the intensity of the sound, with the velocity of the moving object. But we didn't really make any experiments or get this further, but this is a possible way to understand how can a human determine the speed of a car. So there are a lot of things to do here, we think. First of all, we used an omnidirectional microphone, and that maybe add a lot of noise to our measurements. So maybe with a directional microphone that could be improved. We don't know if with the signals that we got, we can just extract some more data in order to find the Doppler shift. And also make some other the experiment with some other cars and try to see if that strange spike peak, in 15,000 hertz it's seen. But there is a problem with the Doppler approach. The Doppler needs to see the moving car, and the problem doesn't say that he's blind, but we need to assume that the binaural hearing, the cop, there can be a small screen between them, and the cop will still know the speed of the car, just drawing a protractor in the ground and just having some good idea of the change of the angles. Because the behavior of the tangent function near to 90 degrees, will not work, right? To know the velocity. Also from binaural hearing theory, we know that from 0 and 180 degrees, also will be not so good for the cop to hear. So something like 45 degrees, something like that, will be something like, and this range will be optimal for the cop hearing. And it's just enough to listen to the car to measure the angles with some reference. Of course, on counting seconds to know the speed of a car. So that's possible. So that's it. And I hope you found